what is meant by a ring, what is meant by a field. That you should remember. We will use that concepts also to prove some theory. First, you should remember what is meant by a group. Group means what all things it will satisfy. I think all of you will remember that. G is a non-empty set and star is a binary operation. Then G star is said to be a group. It should satisfy some condition. What are the conditions? First one, closure law. Second one, it should satisfy associative law. Then third one, it should satisfy associative existence of identity. Then next it should satisfy existence of inverse. Then it is said to be a group. Then after that, what is meant by commutative group or abelian group? It should satisfy one more condition, that is commutative law also it should satisfy. Then we have seen what is meant by a subgroup. Subgroup means what it is subgroup. H is a non-empty set. Then H is subset of a group G. It is said to be subgroup means H also should satisfy all conditions of a group. Then we have one more thing we have seen. A belongs to H, B belongs to H. Then H is a subgroup means what is the condition? A, B inverse belongs to H. If it is a multiplicative group. Then if it is a additive group, what is the condition? A minus B belongs to H. Then field also. You remember what is field? Field means it should be a commutative ring with the unity and every non-zero element should have a multiplicative inverse. These concepts, remember that. First one, group. Group means it should satisfy the conditions. First one, closure law, associative law, identity, inverse. Commutative group means along with that, one more condition, commutative law. Then after that, that subgroup. Subgroup means A belongs to H, B belongs to H. H is a subgroup means A, B inverse belongs to H. Similarly, if it is additive group, A minus B belongs to H. These are things you should remember. Then we will start with vector space. First of all, what is vector space? That definition, almost all question paper you can see for 2 marks. First one, what is vector space? It is F is a field. Elements of F are called scalars and elements of V are all called as vectors. This is, don't think that it is the same meaning as our vectors and scalars. It is one name it has given that. That elements of F is a field and elements of V it is called as vectors. Then we are defining two operations we are defining. First operation is addition. Second operation is multiplication. That addition, that one, it is said to be vector addition and that multiplication is said to be scalar multiplication. Okay, you should remember first one what we have taken. F is a field whose elements are called scalars and V is a non-empty set. In that elements are called as vectors. We are defining two operations. First one is vector addition and second one is scalar multiplication. Then how it is defining vector addition and scalar multiplication? Vector addition is defined as, usually we denote that elements are elements of V. When I say vectors and scalars, you should remember vectors, it is elements of V only. You should not take the meaning of having magnitude and direction. That are meaning, you should not take it. It is name for elements of V. Then usually vectors we denote it by alpha, beta, gamma like that terms. Then scalars we will denote it by C, C1, C2, A, B like that terms we will use it for scalars. Then how we are defining vector addition? Vector addition we are defining as alpha plus beta. If for every alpha beta belongs to B, alpha plus beta should to B. And for every C belongs to F, and for every alpha belongs to B, C alpha belongs to B. Then V is said to be a vector space if it satisfies some conditions. First condition is B plus should be a commutative group or abelian group with respect to vector addition. That means commutative group on that abelian group means what are conditions it should satisfy? Closure law, associative, existence of identity, then existence of inverse, then last one commutative law. Then second condition, C1 plus C2 into alpha is C1 alpha plus C2 alpha, where C1 and C2 belongs to F scalars, and C into alpha plus beta is C alpha plus C beta. This is for every C1, C2 belongs to F, this alpha and beta are vectors. Then C1, C2 into alpha, C1 into C2 alpha. Again, last condition, 1 into alpha is alpha, where 1 is the unity of F. Here also just see, we know that 1 into alpha is alpha. But don't think that this is our 1. This is identity element. Usually we used to denote identity element as E. In rings or groups we were used to denote identity element as E. But here the notation what we are using as 1. It is notation only. It is not actual 1. It is identity element of F. It depends upon what is this field. If it is real numbers means if F is real numbers, then identity element is 1 itself. But if we are taking F as matrices, then that identity element is not 1. What we have to take it? It is depending upon if it is 2 by 2 matrices, we take identity element as matrix 1 0 0 1. It's depending upon it's our field F. Okay, have you understood these conditions? But are you writing, or after that whether you write it up? Whether all of you writing the definitions or not? Writing up? Writing. Okay. Whether have you completed writing? Okay. Then you can start writing. Then I will explain once again. Then we will move on to the problems. I think so. All of you completed? I think might have completed, right? Okay. Then just remember that definition. What are things? First one, F is a field. Then V is a non-empty set. The elements of F are called scalars. Elements of V are called scalars. Vectors. Then V is said to be a vector space. For that, first we are defining two operations in V. First one is vector addition, and second one is scalar multiplication. Vector addition, how it is defined? For every alpha beta belongs to V, alpha plus beta should belongs to V, and for scalar multiplication, C belongs to F, alpha belongs to B, C alpha belongs to B. Then it should satisfy four conditions. First condition, B plus C is a commutative group. Second condition, C1 plus C2 into alpha is C1 alpha plus C2 alpha. And into alpha plus beta is C alpha plus C beta. Third condition, C1 C2 alpha is C1 into C2 alpha. Last condition, 1 into alpha is alpha, but where 1 is unit element or unity of F. We usually denote vector space by V of F. V is vector space and F is a field. Now we will move on to some problems. For rings we were doing problems also. If it is defined, how we will prove that it is a ring like that. Here like that vector space. That means we should show all the conditions we have to show. First one, we are considering one example. Show that the set V, set of all x, y, z, where x, y, z belongs to R, is a vector space over the field of real numbers. Then x, y, z. X, y, z means what it represents. Set of all x, y, z means it is a space. Only x, y is there means it's a plane. Then first case, what we have to prove? If V is a space, then we have to show that it is a vector space. For that, we take all the conditions. First one, what we should prove? B plus is an abelian group. All of you first of all write the question. Show that the set V, set of all x, y, z is a vector space over the field of real numbers. Just write the question. Then we can prove each condition one by one. First condition, what we have to prove? V plus is an abelian group. That means from which one we should start? One, closure law. What is meant by closure law? If alpha beta belongs to V, we should get alpha plus beta belongs to V. Then how it is defined? In V, the vectors are defined as ordered pair x, y, z. Then alpha we can take x1, y1, z1. Similarly, we can take beta as x2, y2, z2. Then we will show alpha plus beta. You know how to add that to ordered pairs. How you add? First one, x1, y1, z1 plus x2, y2, z2 means first we add first element of both the vectors x1 plus x2. Second element, what it will become? y1 plus y2. Next one is z1 plus z2. Then we get alpha plus beta also of the form same form x, y, z. Then x1 plus x2, y1 plus y2, z1 plus z2. That means belongs to V. It is first condition. Otherwise, now all of you listen. After that, I will send this note to your group. Whether is it okay? Otherwise, I will send it this one. Whatever I have discussed, that one I will send it to the group only. Then you can write it after that. Now just listen. But listen. You should listen each step. You should listen it. Then first one, what we have shown? Closure law. What is closure law? If two vectors you should take alpha and beta, then we have shown that alpha plus beta belongs to V. Now, next condition is associative law. We are doing in addition. Then what should be associative law? Alpha plus beta plus gamma. We should get it as alpha plus beta plus gamma. For that, what we take it as alpha? Alpha as x1, y1, z1. Beta as x2, y2, z2. And gamma, what we should take it as 3 by 3, z3. Then alpha plus beta plus gamma. Our alpha is x1 plus y1 plus z1 plus we should add beta and gamma. Then what we get? x2 plus x3, y2 plus y3, z2 plus z3. Again, we have to add that element with the x1, y1, z1. Then what we get? x1 plus x2 plus x3. Second term is y1 plus y2 plus y3. Third term is z1 plus z2 plus z3. Again, since this x1, xy, just see in the V. What is V? It is xyz. xyz belongs to R. R means it is real number only. Then real number, how we can write that? Any real numbers, if we write x1 plus x2 plus x3, we can write x1 plus x2 plus x3. Similarly, y1 plus y2 plus y3, z1 plus z2 plus z3. Then it is same as which one? Alpha plus beta plus gamma. Same type of problems we did in also. It is similar one only. Last two conditions only it's changing. Then next is identity element. What is identity element? It is 0, 0, 0. Then what is inverse? If alpha is x1, y1, z1, additive inverse is, we know that minus x1, minus y1, minus z1. Third condition is, not third condition, in that fifth condition is commutative law. Then what is commutative law? What do you get it as commutative law? Alpha plus beta is beta plus alpha. Then x1 plus x2, y1 plus y2, z1 plus z2, that we can write it as x2 plus x1, y2 plus y1, z2 plus z1. It is same as beta plus alpha. Then B satisfies all the conditions of a commutative group or abelian group. Then first condition is satisfied. B plus is an abelian group. Now we have to move on to the next one. Next condition. What is next condition? Next one is C1 plus C2 alpha is C1 plus C2, C1 alpha plus C2 alpha. Then it is similar like that only. C1 plus C2. Instead of alpha, what we have to substitute? x1, y1, z1. Then multiply. As usual, multiplication only. C1 plus C2, x1. Then second term, what it will become? C1 plus C2, y1. Third term, C1 plus C2, z1. Then expand it. C1, x1 plus C2, x1. Then next is C1, y1 plus C2, y1. Third term, C1, z1 plus C2, z1. Again, next what we will do? We will split that. Consider all the first terms. Then C1, x1, C1, y1, C1, z1. Then next we consider all second term. C2, x1, C2, y1, then C2, z1. Then first one is, we can take C1 as common, then C1 alpha. Second term what we get? C2 alpha. Now we got first one condition. Then in that itself, one more condition is there, but it is C into alpha plus beta. Then C into alpha plus beta, C into, instead of alpha plus beta, you can add it and write x1 plus x2, y1 plus y2, z1 plus z2. Again, we can split that x1, y1, z1 first term, second term is x2, y2, z2. Then C into alpha plus C into beta. Then next condition is C1, C2 alpha, associative law only. C1, C2 alpha, can't say that exactly as associative law. It's similar to associative law. C1, C2 alpha. Then C1, C2, x1, y1, z1. Then similarly, we get that C1 into C2 alpha, you will get them when you simplify that. Then 1 into alpha. But every time you should not write 1 itself, but here it is 1. Why? Because here we have given that it is real numbers only, set of real numbers. Then our identity element is 1 only. Then 1 into x1, z1. That is same as alpha. Then it satisfies all the conditions of a vector space. We will just revise it, not all the steps. What are steps we have seen? Just revise it. First one, what it is given, what we have to prove. V is a vector space over the field of real numbers. First condition, if you remember the definition, I think all of you will be able to prove these problems. These type of problems will be asked for 5 marks. Then first one we should get, it is an abelian group. For that, first condition, closure law, then associative law, then existence of identity, then inverse, then we have seen commutative law. Then we got V plus is an abelian group. After that, we have move on to which one are condition? C1 plus C2 alpha is C1 alpha plus C2 alpha. Then next one is C into alpha plus beta is C alpha plus C beta. After third condition, C1 C2 into alpha is C1 into C2 alpha. The last condition, fourth condition, 1 into alpha is alpha. Then we can say V is a vector space. Next one, what you have to attach in that Google Classroom, this example 2 and 3. Similarly, you should prove it and you should that submit in that Google Classroom. No need of submitting notes, but you should submit this example 2 and example 3. It is similar to our example 1 itself. Just see, first case, it is xy. Only one change, z is not there, it is plain. First we have proved space is a vector space. Here it is plain. We have to prove that it is a vector space. Then third problem, what is the change? Instead of 3 vectors, here how many are there elements? N numbers are there, n tuples are there. Then this is also a vector space. This third question is repeated many times. Only you should change that. Instead of writing x1 y1 z1, alpha what you can take? Alpha is x1, x2, x3, etc. xn. Then beta what we can write? y1, y2, y3, y etc. yn. Show all that conditions. It's easy only. You have to do that and submit it today itself. Then fourth one. Fourth one also repeated question. I think these are very easy problems. Only one thing you should remember, the definition of a vector space. Then how it is defined? Show that V equal to set of all A plus B root 2, AB belongs to Q is a vector space over Q. Then here the elements A and B are belongs to Q. Our field is Q. Q means set of rational numbers. Then just see how is the form of the elements. Only that you should remember. Here how it is defined. The element is of the form A plus B root. Then first what we have to prove that B plus C is an abelian group. Then in that we should prove closure, associative, identity, inverse and last one commutative law. First one we will prove closure law. Closure law means what we have to take it closure law. Two vectors alpha and beta is there. We have to show that alpha plus beta also belongs to B. For that we take alpha as A1 plus B1 root 2. Beta as what we can take it as A2 plus B2 root 2. Now we find alpha plus beta. How we add that two elements? First two elements we will combine, then A1 plus A2. Second, root 2 is common, then we can take root 2 outside. Then element is B1 plus B2. Now just see whether we got this of the form A plus B root 2. Same form we got, then this belongs to V. Then first condition, closure law satisfied. Next one is associative law. How you have to prove associative law? Alpha plus beta plus gamma, what we have to get? Alpha plus beta plus gamma. For that, what we take it as alpha. Alpha, we have to take it as A1 plus B1 root 2. Beta, we should take it as A2 plus B2 root 2. Gamma, what we will take it as A3 plus B3 root 2. Now, we should add alpha plus beta plus gamma. First, we add beta plus gamma. What we get? Beta plus gamma, A2 plus A3, then B2 plus B3 root 2. With that element, we have to add A1 plus B1 root 2. Then A1 plus A2 plus A3 plus B1 plus B2 plus B3 root 2. Again, this is same as we can write it, since these are all elements of Q only. Q set of rational numbers. Then how we get A1 plus A2 plus A3 is same as A1 plus A2 plus A3. Then here B1 plus B2 plus B3. Then we get it as first one is alpha plus beta plus gamma we can write. The next is identity element. Identity element, what it is? 0 only. 0 we can write it in the form 0 plus 0 root 2. Any element that 0 can be written like that. Then it is identity element. Then what will be the additive inverse? A plus B root 2 means what will be additive inverse? It is minus A minus B root 2. Then next one is commutative law. What is commutative law? Alpha plus beta. Alpha plus beta is A1 plus B1 root 2 plus A2 plus B2 root 2. What we get it as? Beta plus alpha. Then it satisfies all the conditions. Then what we can say? It's an abelian group or commutative group. Now, next condition. You should remember the conditions, then you will be able to prove everything. Condition is, what is the condition? C1 plus C2 alpha is C1 alpha plus C2 beta. Then what is that? C1 plus C2 into alpha. What is our alpha? A1 plus B1 root 2. Just multiply. First one C1 into that term. Next is C2 into that term. Then we can write this is same as C1 alpha plus C2 alpha. Next one, in the second one itself, C into alpha plus beta. What it is? C into alpha plus beta? C into add alpha and beta. It is same as A1 plus B1 root 2 plus A2 into B2 root 2. It is same as C into first term plus C into second term. Or we can write C alpha plus C beta. Next last condition, C1 C2 alpha, C1 C2 into alpha. Or we can write C1 into C2 this term. Or we can write C1 into C2 alpha. Next is 1 into alpha. But here also, what will be our unity element? Whether 1 will be 1 itself, 1 is means our unity only. Unity in set of rational numbers. What is that set of rational numbers? Also unity element or identity element is 1 itself. Then 1 into A1 plus B1 root 2. It is same as A1 plus B1 root 2. It is same as alpha. Okay, we will just see what are the conditions. First one, what we have that question, A plus B root 2. You should remember how to take the form of the elements. Then you should remember all the steps. Then I think all of you can prove that, I think so. Alpha, what we have to take it as? A1 plus B1 root 2. Beta, what we can take? A2 plus B2 root 2. Gamma, we can take it as A3 plus B3 root 2. Then what all condition? First one, we will prove that it is a commutative group. That means we will prove closure law, associative law, then after closure law, associative law, identity element, then inverse, then commutative law, then it will become a commutative group. Then second condition, what it is the formula? C1 plus C2 alpha is C1 alpha plus C2 alpha. Then third condition is not third condition. In second condition only, one more condition is there. C into alpha plus beta. It is C alpha plus C beta. Then third condition, what we get it as third condition, C1 C2 into alpha is C1 C2 in C1 into C2 alpha. The last condition is 1 into alpha is alpha. I hope all of you understood this concept. Then shall I move on to the theorems? Have you understood whether I should explain it? Can I move on to next one? Okay. This first theorem also, it's very easy. In rings also we have proved like that one theorem solved. I think you will be remembering first theorem. But don't think that this also university question only. It is university question for 5 marks. And ask all the conditions. Here 7 conditions are there. But all these 7 conditions won't be asked. That 3-4 conditions will be asked. But it is very easy. The only first one we will prove it. But to remember that, you should write and practice only. Otherwise, won't be able to remember. First one. First condition what it is. B is a vector space means we have to prove A into 0 equal to 0. That we know that A into 0 is 0. But how we prove that A into 0 is 0? By using all the conditions of a vector space. For that, we have to use the definition of a vector space and we should prove each one by one. Then, first we will prove it. A into 0 is 0 for every A belongs to F. For that, first what we will take that A into 0, 0 plus 0, what we can write? 0 plus 0 equal to 0. All the things, first one also, second one also, we will take this one condition only. 0 plus 0 equal to 0. Then next what we will do, we multiply with, we want to get A into 0. For that, we multiply both sides with A. Then what we get, A into 0 plus 0 equal to A into 0. But 0 is additive identity. Then what we can write it as, first one is A into 0 plus 0. That can be written as A into 0 plus A into 0. Y means this is of the form A into alpha plus beta. A into alpha plus beta is same as A alpha plus A beta. Then since 0 is the additive identity, A into 0 can be written as A into 0 plus 0. Again, by left cancellation law, what we can write? A into 0 will be cancelled. Then next what we get? A into 0 is same as 0. It's very easy. How we are getting? First what we have done? 0 plus 0 equal to 0 written. After 0 plus 0 is 0 means next what we multiply both sides with A. Then A into 0 plus 0 is A0. Then that can be written as A into 0 plus A into 0 equal to A into 0 plus 0, since 0 is additive identity. Again, by left cancellation law, what we get? A into 0 is same as 0. Next, we will move on to the next one. 0, next one what it is? 0 into alpha equal to 0. This also, instead of A into 0, here what we have to, same steps only one change. Instead of multiplying with A, what we should do? We should multiply with alpha. Then how we can write? 0 plus 0 is 0. Then what we can write it as? 0 plus 0 into alpha. We are multiplying both sides with alpha. Then 0 plus 0 into alpha is 0 alpha. Again, like last one, what we can write? 0 alpha plus 0 alpha is 0 alpha plus 0. since 0 is additive identity. Again, by left cancellation, what we get? 0 alpha equal to 0. Okay, now we will move on to the third one. What is third one? Third one, usually it will be asked for third one, fourth one are usually asking separately for 2 marks question also. Third and fourth one. Third one is a into minus alpha equal to minus a into alpha equal to minus a into alpha. Then we will prove this as two conditions. First condition what we prove, a into minus alpha. I will try to write it, but I don't know how my handwriting, it won't be so good. I think you can see a into minus alpha. What we will prove, instead of proving directly, first what we will prove that a into minus alpha plus a into alpha equal to 0. This is first condition we will prove. Understood? First condition and third condition. What we have to prove? A into minus alpha equal to minus of a into alpha. Instead of that, what we prove? A into minus alpha plus a alpha equal to 0. Like that, second condition and third condition. What we have to prove it as? Minus a alpha equal to minus of a alpha. Or we write plus a alpha equal to 0. We will prove it. These two conditions we prove. Then first one is, what is that? A into minus alpha plus a alpha. This is same as a common, we can take it. Then it is alpha plus minus alpha. Then alpha plus minus alpha is same as alpha minus alpha. But what is alpha minus alpha? It is 0. Then what is a into 0? A into 0, we have already proved that it is 0. Then from this what we get it as? A into minus alpha is the additive inverse of a alpha. Or we can write a alpha is the additive inverse of a into minus alpha. Or we can write a into minus equal to minus of a alpha. I hope you understood. All of you understood. First one what it is? We are taking first condition and third condition. To prove a into minus alpha is minus of a alpha, what we prove that a into minus alpha plus a alpha is 0. For that, we take a in a alpha plus a into minus alpha. Then a is common, alpha plus minus alpha. It is same as alpha minus alpha. But what is alpha minus alpha? It is 0. Then a into 0 is 0. Then we get it as a into minus alpha is minus of a alpha. Next one is a alpha plus, that means second condition and third condition. That is a alpha plus minus a of alpha. Again, alpha is common. We can write a minus a. A minus a is 0. Then 0 alpha also we know that 0. Or we can write a alpha is the additive inverse of minus a into alpha. Or can write minus a into alpha is minus of a alpha. It is our third condition. Then fourth condition. What is fourth condition? Fourth condition is a into alpha minus beta. That we have to prove that a alpha minus a beta. It's very easy steps, but you should remember it. A into alpha minus beta, how we can write? A into alpha plus minus beta. That is same as a into alpha plus a into minus beta. But a into minus beta is same as minus a beta. Then we get a alpha minus a beta. Shall I move on to fifth one condition? Fifth one. What is fifth one? A alpha equal to 0 means we have to prove either a 0 or alpha equal to 0. A alpha 0. We suppose a not equal to 0. A not equal to 0 means what we get? A inverse exists. Why? A not equal to 0. I am writing A inverse exists means why is given given that f is a is a scalar. Scalar means it belongs to f. What is f? F means field. Then field means what it is? Commutative ring with unity, and every non-zero element has multiplicative inverse. Then whenever we are writing any element from F, it is non-zero means it will have a multiplicative inverse. Then A not equal to 0 means we can write A inverse exists. Then we will multiply both sides with A inverse. Then A inverse of A alpha. Then right hand side also we should multiply with A inverse. Then A inverse of A alpha as A inverse 0. Then A inverse into A, we can change it into alpha equal to 0. A inverse into A is identity element. Usually identity element in this vector space we are denoting by 1. 1 into alpha. But 1 into alpha is 0. But what is 1 into alpha? Alpha 0. Then A not equal to 0 means we get 0. Similarly, we can say alpha not equal to 0 means what we get? A equal to 0. What you have to do for that? You have to alpha not equal to 0. Then you will get that next condition. That no need of proving that A not, then we get that A equal to C, that either A will be 0 or A 0 means what we can write directly? Alpha should be 0. Because alpha is a vector, A equal to 0 means alpha also should become 0. Now we will move on to the sixth condition. A alpha equal to B alpha. Then A not equal to 0 means, sorry, not A. Alpha not equal to 0 means we have to prove that A equal to B. A alpha equal to B alpha. Alpha not equal to 0. Then A alpha equal to B alpha, we can write A alpha minus B alpha. Or we can write that A alpha minus B alpha. A alpha minus B alpha 0. A alpha minus B alpha equal to 0. Or alpha we can take it as common. Then what we can write? A minus B into alpha equal to 0. Then alpha not equal to 0 means which one will become 0? A minus B, it should be 0. Then we get A minus B 0 means what we can write it as? A equal to B. Then seventh one. What is seventh condition? A alpha equal to A beta. A alpha equal to A beta. Then we have to prove that alpha equal to beta. Then what you get that? A alpha equal to A beta means we can write it as A alpha minus A beta equal to 0. Then this as same as A into alpha minus beta equal to 0. That means what we can say? A not equal to 0, what should be 0? Alpha minus beta should be 0. Or we can write alpha equal to beta. Okay. Now we have proved all the 7 conditions. I think only 7 only question. Just let me check whether it is 7 conditions only. Okay. 7 conditions only. We have proved all the conditions. I hope all of you understood. It's very easy one only. First one, first to prove first 2 condition, what you have to remember it? A into 0, 0 and 0 into alpha 0. To prove that, we take the condition 0 plus 0 equal to 0. Then we, first condition, we multiply left side by A. In the second condition, we multiply with that alpha. Then we will expand it. Then third condition, to prove that third condition, how we are taking as A into minus alpha is minus A into alpha equal to minus of A alpha. Then we will take first condition with the third condition. That means A into minus alpha plus A alpha equal to 0 we prove. Similarly, we prove minus A into alpha plus A alpha equal to 0. Then to prove fourth condition what we are taking? A into alpha minus beta is A alpha minus A beta. That means how we have to prove that one? We write A into alpha minus beta as A into alpha plus minus beta. Then we will expand that. A alpha plus A into minus beta. The next step what we can write? A into minus beta is same as minus A beta. Now to prove fifth condition, how we are taking A alpha equal to 0, either A 0 or alpha equal to 0. If A equal to 0, then alpha also will be 0. Next condition, A not equal to 0. Then A inverse exists. We will multiply both sides with A inverse. Then we get alpha equal to 0. Sixth one, how we prove? A alpha equal to B alpha. Then what we have taken? A alpha minus B alpha equal to 0. Again, alpha we have taken as common. A minus B into alpha 0. But alpha not equal to 0, it should be B. Similarly, for A alpha equal to A beta, which one we will take it as common? A we will take it as common. Then alpha minus 0, alpha equal to B. Now we have completed theorem 1. Now one more definition is there. We will move on to that definition. Definition of subspace. It is similar to our A into alpha minus 1. How we prove? A alpha equal to B alpha.